Picture the Earth roughly 4.5 billion years ago, barely 100 million years old, still glowing from its own formation, its surface a shifting mix of molten rock and thin, unstable crust. A Mars-sized object, a planet in its own right, is on a collision course with it. Not a graze, not a near miss, a direct, glancing impact violent enough to melt rock, vaporize entire sections of both worlds, and throw an enormous ring of debris into orbit. That debris, over the following months and years, slowly pulled itself together into a single object. We call it the Moon. That's not speculation dressed up as science. It's the leading explanation for how the Moon actually formed, called the giant impact hypothesis. And it means the single most familiar object in our night sky exists because of a cosmic collision that could very easily not have happened at all, or could have happened just slightly differently and produced nothing recognizable in orbit whatsoever. Scientists gave the impacting object a name, Theia, after the mythological mother of the moon goddess in Greek tradition, and the physics behind the idea has held up remarkably well against decades of scrutiny. Rock samples brought back from the Apollo missions show striking chemical similarities between moon rock and Earth's outer layers, exactly what you'd expect if the moon really did form from material blasted off both worlds during that collision, rather than being an object that formed somewhere else entirely and simply wandered into Earth's gravity later. The angle and speed of that impact mattered enormously, too direct, and the two bodies might have simply merged into one larger planet with no debris ring left over at all. Too shallow, and Theia might have grazed past without leaving enough material in orbit to ever coalesce into a moon of any real size. Here's what that moon actually does for us today, because most people underestimate how much depends on it. Earth's axial tilt, the 23.5-degree lean that gives us seasons, isn't naturally stable on its own. Without something large and gravitationally significant nearby to steady it, a planet's tilt can wander chaotically over long timescales, swinging unpredictably instead of settling into the reliable rhythm we take for granted. The moon's gravity acts like a kind of anchor, keeping Earth's tilt locked into a narrow, predictable range for hundreds of millions of years at a stretch. The moon also drives the tides through the simple pull of its gravity on Earth's oceans, and those tides do more than move water up and down twice a day. Some biologists studying early evolution point to tidal zones, the shifting boundary between wet and dry land, exposed and submerged on a predictable daily cycle, as a plausible training ground for the first organisms that eventually adapted to survive outside water entirely. Organisms stranded briefly in shallow tide pools during low tide faced real evolutionary pressure to tolerate short stretches out of water, breathe air even briefly, and cope with temperature swings that fully submerged sea life never had to deal with. Repeat that daily pressure across millions of generations, and you have a plausible stepping stone toward the eventual jump from ocean to land that shaped the entire later history of life on Earth. And the moon has been quietly slowing Earth's rotation for billions of years through tidal friction, which is why a day on Earth used to last only about 6 hours shortly after the moon formed, gradually stretching to the 24 hours we experience now. That slowdown happens because the moon's gravity drags slightly on Earth's oceans as the planet spins beneath it, creating friction that bleeds off rotational energy over unimaginably long stretches of time. A process so gradual that a single human lifetime never notices it, but one that has fundamentally reshaped the length of a day several times over across the planet's history. So that's what happened and what it built. Now, otherwise. Picture that same early Earth, except the object we call Theia never quite lines up for the collision. Maybe its orbit differs by a fraction of a degree. Maybe it forms slightly later or earlier, missing the window entirely. Either way, no impact, no debris ring, No moon ever coalesces in Earth's orbit. Our planet spins alone. The first thing to go is that stability. Researchers who've modeled Earth's axial tilt without a large moon to anchor it have found the tilt could plausibly wander anywhere from nearly 0 degrees to over 50 degrees, chaotically, over timescales as short as a few million years. Geologically speaking, almost no time at all. Compare that to Mars, which has no large moon of its own and shows exactly this kind of unstable, wandering tilt over its history, swinging by tens of degrees over relatively short geological windows. A planet with no seasons, one era, and brutal, near-sideways seasons, swinging entire hemispheres between extreme heat and prolonged darkness the next, doesn't offer anything close to the kind of stable, predictable climate window that complex life seems to need to slowly evolve over hundreds of millions of consecutive years without being wiped back to the drawing board. Picture what that would actually feel like on the ground, if anything survived long enough to feel it at all. An ice age settling in over a few thousand years, followed by a scorching, nearly tropical stretch just a few 100,000 years later, followed by another dramatic swing in the opposite direction. Not the gentle, multi-thousand-year climate cycles our actual planet experiences, but something closer to a planet permanently lurching between extremes, never settling long enough for any one ecosystem to fully establish itself before conditions shifted dramatically again. Rotation speed changes too. Without lunar tidal friction acting as a brake, Earth likely keeps spinning much faster for far longer, possibly still completing a full rotation in something closer to 6 to 10 hours today, rather than 24. Days that short compress everything: weather patterns, wind speeds driven by a much faster spinning planet, and the basic day-night rhythm every living thing on Earth has built its biology around. A faster spin also means stronger Coriolis effects, shaping weather systems, likely producing more numerous, more compact storm systems compared to the broad, slower-moving weather patterns our actual 24-hour rotation allows. Whatever evolved to survive on this otherwise version of Earth would be adapting to a planet that behaves, in some fairly fundamental ways, unrecognizably different from the one we actually got. The tides shrink dramatically too, left with only the sun's much weaker gravitational pull to work with, roughly half the tidal force the moon currently provides, producing tides so subtle that many coastlines would barely show a noticeable difference between high and low water across an entire day. That quieter, calmer coastline removes exactly the kind of unstable, twice-daily wet and dry cycle some researchers think helped nudge early life to experiment with surviving outside water in the first place. It doesn't necessarily mean life never makes that transition in this otherwise scenario, but it removes one of the more compelling environmental pressures that may have helped speed it along in our actual history. Even the night sky changes the story. Our actual night sky gets a meaningful amount of its brightness from reflected sunlight bouncing off the moon, which matters more than it sounds like it should. Countless nocturnal species evolved their hunting, mating, and migration behavior around lunar light cycles. Some coral species time mass spawning events to specific lunar phases, and many nocturnal predators rely on moonlight brightness to hunt effectively, timing their activity around exactly how much light happens to be available on a given night. Remove the moon, and every one of those finely tuned, lunar-linked behaviors loses the environmental cue it evolved around in a world of consistently darker, more uniform nights. Human history is soaked in lunar cycles too. Nearly every ancient calendar system, from Babylon to early Islamic and Chinese traditions, tracked time using the moon's predictable phases, long before anyone had a reliable way to track the sun's position with the same precision. The moon's roughly monthly cycle gave early civilizations a natural, easily observed unit of time, larger than a day, but smaller than a year, long before anyone had the astronomical tools to calculate a solar year precisely. Remove the moon, and you remove the single most convenient, visible clock nearly every early human civilization built its earliest sense of time around. An otherwise version of history, where the very concept of a month might never have emerged the same way, or might have taken far longer for any civilization to develop an equivalent substitute. So maybe the strangest part of this whole otherwise scenario isn't the wilder climate swings or the shorter days. It's that the very stability we associate with normal Earth, steady seasons, a slowly turning 24-hour clock, oceans that rise and fall in a pattern predictable enough to build entire civilizations' fishing and farming schedules around, was never actually guaranteed by anything except one violent, half-chance collision happening to land at just the right angle, at just the right moment, 4.5 billion years ago. It's worth remembering that the moon isn't finished changing our story yet either. It's still drifting away from Earth today, roughly 1.5 inches farther every single year. A measurement scientists have tracked with remarkable precision using reflectors. Astronauts left on the lunar surface during the Apollo missions, bouncing laser beams off them from Earth and timing exactly how long the light takes to return. That slow drift is loosening the exact grip that keeps our tilt and our days as stable as they currently are. Nothing dramatic happens on any timescale that matters to us personally. We're talking hundreds of millions of years before the effect becomes significant, long after the sun itself will have changed enough to make the question somewhat academic. But it's a strange thought to sit with. The stabilizing anchor this entire episode has been describing was never permanent in the first place. It's a temporary arrangement, slowly working itself loose on a timeline so long it's easy to mistake for forever. If the single object responsible for the climate stability that allowed complex life the time it needed to evolve was itself the product of one half-chance collision, it raises a question worth carrying into the next episode. How many other stable, permanent features of our world are actually just temporary arrangements held together by something that happened to go right once, a very long time ago? That's exactly where we're headed next time on Otherwise, into the accidents of physics that quietly made a habitable planet possible at all. Subscribe and find out what else almost didn't line up.